Now if we do acyl substitution under acidic conditions, all the intermediates need to have a positive charge or be neutral. Nothing can have a negative charge. We can't have a negative charge or a strong base present in acidic conditions. Let's think a little bit about the reactivity of the things that we are working with here. We know that alcohols like water are poor nucleophiles, and we know that a carbonyl compound like an aldehyde or ketone and also a carboxylic acid or acid derivative is a moderate electrophile. Okay, so it turns out that if you put these two things together and come back 20 years later, what you see is very little has actually happened because we have such a poor nucleophile. So either you have to make this a better nucleophile or make this a better electrophile. And under acidic conditions, we can't make something a better nucleophile, so we're going to have to improve the electrophilicity of the carboxylic acid. So, as you are used to seeing in acid-catalyzed mechanisms, the first thing that happens is that protonation occurs. So, if protonation occurs, then what we have here is a much better electrophile. The reason it's much better is that we have this resonance structure that is almost equally important as the first one we've drawn, that has a positive charge on the carbon. So here we had a tiny bit of a partial positive charge on carbon, and here we have a couple of resonance structures that are probably about equal in importance, both of them having a positive charge on, this one having a positive charge on oxygen, which isn't good, but it has complete octets. Here having a positive charge on the more electropositive carbon, but an incomplete octet. So bottom line is we have a much better electrophile here. So very good electrophile because it has a full positive charge on it. So now our poor nucleophile, after we did this first step, which is protonation, our good nucleophile, our poor nucleophile can come in and add more easily. So we can show this coming in either one of these resonance structures. We're adding it, and we are breaking the pi bond if we're attacking this resonance structure, and we have an intermediate that we are producing here. That is our tetrahedral intermediate. So here is our leaving group, our OH, and here is the nucleophile that we have just added here that now has a positive charge on there. So we did protonation, now we are doing addition. And what do you think we do in the next step? Protonation, you do something, deprotonation. So in the end, we have to get rid of that hydrogen, and so before we add a proton onto something else, we have to take this one off. So if we deprotonate there, then we have our tetrahedral intermediate here that is neutral. Deprotonation. Okay, so we did a protonation, an addition, and a deprotonation, and we have completed the first half of the mechanism.